Hello, I'm Sam Highfield and I'm doing the Royal Yachting Association Day Skipper course for sailing. And it's a really great course, I've really enjoyed it, it's really thorough and precise, except for one part in my opinion, and that is on course to steer. Now, it's my own personal policy to never complain about something unless I can offer a better solution. And I'm pretty sure that I have a better solution right here. It builds on top of the great work that's already been done on this subject. So let's take a look. This is the new method for course to steer that I am proposing, and I'm calling it the multiple plot method. And you can see a little preview of it on the right here with the current method on the left there. This has a few advantages over the current system, and that is there's no more guessing. That's very important, I found, because the rest of the course is so well done and so precise that when we suddenly got to start guessing things, I thought, well, there must be some kind of surefire way of doing this. It just seems at odds with the rest of the course that's so precise. And then to start basing measurements and later on guessing scales of these triangles based on the guess, it just seemed a bit lacking to me. So anyway, it works in every situation. That'll be very obvious in the next example I'm going to give, and it makes it a lot easier to read the tidal atlas. So let's go and jump in and explain it with an example, because I find that's the best way to explain it. So this here, this example that I'm going to give is actually from the training material, the course material. So this is the course to steer section 23, and it's going on about plots of more than 1 hour, where we've got to go from this buoy here to this one over here, a distance of 9.58 nautical miles. So I've gone and plotted that on this chart here. So exactly the same from that buoy to this buoy. And I've done it with the two different methods. So let's go through the original method first. So first of all, okay, I've already drawn this, but on the course it said you've got to guess, and that is the method, isn't it? You've got to guess how long the journey is. Now, I've already said my piece about this, about how can you guess what if there's a lot of strong opposing tides against your boat. It could take 10 hours to go this way if you're only making, say, 0.2 knots against the tide. So anyway, well, let's go and follow this through anyway. So the method is, we've guessed that there's going to be 2 hours. So we've got two sets of tides here, okay? So first one at 345 degrees. We can actually overlay the tidal atlas here. So if you notice, if I go between the two, all the land masses line up pretty well. The course stays in the same position, but it allows us to choose a good starting one. So from here, a good tidal stream to use is this one here. So 345 degrees at 0.9 knots, so we're in Neaps. Okay, so we'll go and plot that one. We'll go and plot a second one, okay? So we've also guessed that we're going to use this tidal stream as well. So we're going to guess that after the first hour, we're going to be able to use this one, okay? And then with a third one if we need it. Okay, so we draw this tide, then we draw that tide, and then our water track, which is 2 times 4 knots because it's 2 hours, right? So that's 8 knots, and that intersects this line here, and that gives us a speed over ground. And then you use this calculation here, which is a distance divide a distance to give a time, as opposed to time equals distance divided by speed. I'm guessing using like a ratio of this line up to the full length of the line. I have a problem with that, and I'll explain it later on. So anyway, there we go. So we've got this time here. Let's look at the new method, okay? So we're going from here to here. Let's presume these haven't been drawn, okay? So I don't have to guess at all how long this journey is going to take. So I'm just going to draw in 1 hour of tide. So I do that, 345 degrees at 0.9 knots. So I draw that one. The boat speed is 4 knots. So this line is 4 knots long. Where they intersect is our speed over the ground. Okay, so if I overlay this, we are here after 60 minutes. Let's go forward another hour, okay, to 2 hours. So now, see, if I'm going to go along this line, it might make sense to use this one here, but at least I can see exactly where I am on this tidal atlas. Obviously, you can't overlay this directly because this is computer graphics. I can do this, but you have a really good idea of where you are and which tidal stream to use. So again, it's a lot more precise, takes guesswork out of it, and we know we're exactly here, whereas here we could be anywhere along this line. Okay, and then when we end up, we're going to end up just before here, which does mean we need to take into account a third hour, which we haven't done on this one. Okay, and then we draw another triangle again, taking into the third. So we can see that we're here. I think, what tide should we use next? Well, this one is quite close to this one. So it's 275 degrees, 0.8 knots. So that's what I have here. And then what you do is you can go and find your time by adding all these up. So for 60 minutes, and this is how course to steer should be given. I don't think an average is very good, because let's take a look at this. Course to steer is how you steer straight in spite of the tide, given your current speed. So you want to make a straight course. You don't want to make a curve. So at this point, the tide is 345 degrees at 0.9 knots. Okay, so that means you must steer at this angle for this first hour of tide. So that's 316.96 degrees. And I'll explain how this is so precise later on. Well, I'll give you quick previews, because I've made a calculator, which you can use, by the way, to calculate this as well. So we should be at 317 degrees, but actually we're going to be doing it at 312 degrees. So we're not quite on the right course. So we are going to go in a bit of a curve, aren't we? Okay, so that's the problem with this one. And then the next average tide for the next hour is 309. Okay. However, so we should be at 309, but actually we're making a course of 312. So again, it is off again. And then finally, we got to go CTS as 330 degrees. Okay, it's only for 5.74 minutes. Okay, but that could have been a lot more, you know. I think you should really calculate it for the entire length and not just presume that these tides are going to hold for the last 6 minutes. Because what if at the end of this, there's a really strong tide that goes against you and actually stops you from ever getting there, you know? So that's how it should be. So 60 minutes of this, 60 minutes of that, and then 5.74 minutes of that. And that is your course to steer. They actually average out pretty similar, but let's go and put this through the calculator here that I've created. So that's the website address, samhighfield.co.uk /course-2-steer-calculator. So bearing to waypoint, I measured that at 322 degrees. Distance to waypoint is 9.58 nautical miles. The boat speed is 4. Now it's already given us a calculation, because presuming no tide, okay, slack water, this is how fast you get there. Okay, so if you want to put in a tide, so 345 degrees at 0.9 knots, 0.5, so 3.345, 0.9 knots. Okay, so that gives us this, and it gives us a warning. You must add at least one more tide to accurately calculate this journey. Okay, you don't know how many hours it's going to be, because you need to enter in the tide. So you need to enter one more hour of tide. That's good, because we know if we plot this on our chart, we're here, and then we can look for our tidal atlas and find the next tide that we should use. Okay, so that's 026 at 1 knot, 1.0 knot. So at this point, this is as far as we've gone with the original example, okay? So this is how I've got your average here used in the course material. You've got 312.8, and that's the time there. So you call it 126 minutes, because obviously that's really close to 126 minutes, 2 hours and 6 minutes, okay? However, it's also saying you must add at least 1 hour of tide to calculate this journey, which is correct, isn't it? Because we haven't taken into account a third hour of tide for this last maybe 6 minutes, okay? So let's go 275 at 0.8 knots. Okay, and now we've arrived. The warnings have, disappeared. And there we go, 3.1, that's all these values here. Now, I have provided, reluctantly, a course to steer average here, but what you should do is click the breakdown, and it gives you kind of like a Google Maps directions, an automatic breakdown on how to steer, okay? And I think altering your course every 60 minutes is not so bad, really. So for 60 minutes, there we go, 316.96. For 60 minutes, go there. So basically, we're steering a straighter course, okay? Before I said, what if there's a really strong course, a really strong tide against us, okay? So 026, sorry, so 275, that is going towards us. So let's send it the other way. Let's send it to 90 degrees, okay? And let's go and increase this. Okay, I'm just going to zoom out on this here so we can get it all in. So, I mean, if it did go higher, I know, let's say 6 knots, whatever, it will actually tell us an error here because you'll say, and it'll even tell us where the error is. So the tide at hour 3 is too strong against our current boat speed for this course. So if that did come up, how low can we go with that? 5, 4.3, 4.2. So 4.1 knots, okay, is enough to throw us, make it so we can't actually get there, okay? So that's why I think it's important to calculate the entire course. So a tide of 90 degrees at 4.1 knots will actually mean that our boat can't get there, okay? So let's go to the next example, which is more dramatic. It was in the very first question.
Plot a course to steer.
Okay. So
if you've plotted it correctly.
So basically, this is the course here, and I was looking at, okay, so this is the kind of tides we're looking at. Now, I was looking at the tidal atlas. So this is 6 hours before, 5 hours before, and 4 hours before. So 6, 5, 4, and we can see the tides changing there. So looking at this one here, okay, which was used in one of the examples and the questions here. So it's the very first course to steer question in the course material. Okay, so that's kind of in this area there. So I thought, all right, I'm going to have a look at this. So here we can see that this one it changes course quite dramatically over 1 hour. Okay, so we go from that direction to the opposite direction, and then we carry on going on for another hour there. So I thought, right, let's go and plot this. Okay, so what if we plotted this course? So bearing to waypoint is 50 degrees, which is the same as in the example question. Distance to waypoint is 8.6 miles, same as before. I've slowed the boat speed to 3 knots. So first, we're going to use the original method. I can even zoom in a little bit here, and there's a reason why I've done thin lines that become obvious in a moment. So let's plot the first one, 304 degrees at 1.5 knots. Okay. Let's do the second one, 108 degrees at 0.5 knots, so quite close there. And then we've done the third one, okay, 122 degrees at 1.0 knots. And then we carry on, do our water track. And there we go. And you can see that we've done exactly as the method says. But because the tide has turned back on each other and we're averaging out the tide, the course to steer is basically the same as the bearing to waypoint. So for 3 hours, we've got to go and travel pretty much in a straight line. When the tide is going, you know, all over the place, it just doesn't work. Okay, in this situation, and I think in many situations, the course to steer averaging thing, it just doesn't work. Let's go and take a look at the method again with, the course again with my method here. So the first one, 304 degrees, 1.5 knots, and then you draw your water track, and then you get your course to steer 78.73. Then we start again. So next one is 108 degrees. Remember, we've not had to guess 3 hours here. We're just doing 1 hour at a time. 108 at 0.5 knots. Okay, and that gives us a course to steer of 41.87 degrees. And then the third hour, which lands bang on, okay, on 3 hours. And that's a course, so 122 degrees on the tide, 1 knot. And every time, obviously, this is 3 knots long on the water track here. And that's what we get there. So what we can do is we can compare that with this. And which one is more useful. Okay, now I have given a course to steer average here, but I've said it's not very useful because that would again give us 50.72 degrees when really hour by hour you need to go and put these in. Okay, now we can go and put this in the calculator. Okay, so bearing to waypoint is 50 degrees true, 050. Obviously it corrects it to 050 there. Distance to waypoint is 8.6. Boat speed is 3. So that's already given us a time there. So the tide first hour is 3:04 at 1.5 knots. It's telling us you've got to add at least 1 more hour of tide, so we'll do that. Second hour is 1:08 at 0.5 knots. Okay, we still need another hour. So, and the third one is 1:22 at 1 knot there. Okay, so obviously we're pretty much bang on at 3 hours there, which is 180 minutes. The breakdown is done automatically for us. Okay, let's take a look at this here. And obviously those are the results that we get there. So basically what I'm saying is in every situation this method works, okay? Averaging out a course I don't think is a good idea. Okay, it generally works. It works for 1 hour, but then doing this whole trying to plot all the tides in one, I think it's just too fragile, and it gives you a result that's not useful, as we can see here. Okay, so that's the method there. I'll just do a quick recap. Okay, so basically, there's no more guessing. At no point did I ever have to guess. It works in every situation, as you can see here. Okay. Easy to read the tidal atlas as well. As you can see, when we're going and plotting, you know, all these things here, you know, where are we on this line? Which tidal stream to use? Well, here it is obvious. Okay. So that's it for the actual method. There's a few more things that I wanted to just point out, which I don't think needs to be changed. As I said, I really love this course. You know, I've had a great time. It's just this course to steer that jumped out as a bit of a question mark. So the only thing I can say extra is, so let's go and take a look at what the course says about the actual method here, because it raised a few question marks with me. It does work, that's for sure, but I think the procedure is said, but not the principles behind it. So let's take a look.
Imagine we want to navigate from a fix, A, to a destination, B, a distance of approximately 6 miles, and at the same time the tide is setting roughly perpendicular to our required ground track at 2 knots. Start by drawing the ground track from A to and through B and mark it with 2 arrowheads, which is the symbol for ground track.
Now, this whole thing of, I've got a point to say about this as well, because it says later on that the number one thing that people get wrong in the exam is, well, we'll see in a moment, is basically thinking they have to connect the triangle to the end of this point here or directly to the waypoint.
Now, consider roughly how long it's going to take you to get to B.
Now, consider roughly, you know, this is what makes a big question mark. And obviously this new method removes the need to guess and then start basing everything on guesses and such. It replaces it with certainty. But let's carry on anyway.
It's going to be half an hour, 2 hours. Keep it simple. It does not have to be exact. In this example, we're going to estimate that our boat speed will be 5 knots. So it's going to take just over an hour, and we'll draw a 1 hour plot. So plot a 2-mile tidal vector way from A and mark it with 3 arrows, the symbol for tide. We'll call the end of the tidal vector point C. We then arc the distance we will travel in an hour, which is rather obviously 5 miles, from point C to intersect the ground track to find point D.
Alright, so this is the thing. Okay, so we're drawing this line here. And I think, well, okay, so this line, I get that one. This line, I get that one. But then it has to intersect this line. I thought, what on earth is going on here? Okay.
Now plot your course to steer CD and measure it with your protractor. In this case, it's 0 to 7 degrees true.
But it does work. Now, the thing is, I was looking at this and all this thing, and think what it kind of links there, it doesn't go to the end. What on earth is going on? And I was looking at it and I thought, you know what? I know what this is. This is basically a resultant forces vector diagram, like we used to do in school, and they're using the parallelogram method, okay? So I was thinking, that's what it is, isn't it? So that is what it is. So I'll explain further about, what this method is. So imagine, this is kind of like a question we could get at school. So imagine you've got a big boat here and you've got two tugboats, and one of them is pulling with a force of 2.3 newtons, or say 2.3 knots in this direction, and then you've got 8 newtons of force pulling on this one, okay? And then what you got to find out is what's the resultant vector, okay? What on earth is this, okay? So there's a few ways you can do that. So what you do is you go and move these two vectors end on end, okay? And then what you can do then is, if you know the angle between them, you can basically go and figure out this. And so it's like a triangle. You've got two sides, an angle, and then from that you can work out all the other sides and all the other angles from this. Now you can do this with the sine and cosine rules, but if this scares you off, or you just don't like to do this kind of thing, there is a quicker method you can use, especially if you've got an accurate pencil drawing, and that is, if you draw a parallelogram, then the diagonal between these two corners, there we go, and then that will basically be the resultant force, okay? So you didn't have to do any sine rule stuff or anything like that. You could just draw a parallelogram, and then the diagonal is there, and you can measure the angle of this and measure the length of this, and that will give you your vector. So the heading and the magnitude, which is in knots in this case. So when we overlay this on the chart, that's exactly what we have there, and that's basically what we've done. It's basically a resultant forces diagram. Now, obviously, if we go and show this here, we have this angle, okay? We have the tide angle, but we have no idea what this angle is here. In fact, it could be anything, couldn't it? Okay? But we do know that this is definitely 8 knots. This is definitely 2.3 knots. It's got to be somewhere along the straight line. So where it intersects, okay? Then it'll stop eventually. That's what it is there. So this is basically a way of avoiding, some scary looking maths here. You can just draw it, and that's the method that's going on here. So that's the principle behind what we're doing. Something else I'd like to point out as well is this vector, it doesn't matter what the time is. So let's say we're doing a journey of, 10 hours. As long as we keep our speed of 8 knots on our boat, and the tide is always 2.3 knots, say for 10 hours, then our resultant force will always be 6.8 knots in the same direction. Now, the reason why I think a lot of students make the mistake of connecting this point here straight up to the waypoint is because effectively what we're doing is we're actually overlaying two separate things on the chart together. So I'll show you what I mean by that. So if you lift this off, this is basically just to do with speed, and forces. Time and distance doesn't necessarily come into it, but because we're using the same units for everything, knots, this line will actually be 6.8 nautical miles long, okay? Because it's 6.8 knots and the time is 1 hour. So what you could really do is you could even plot this on a separate piece of paper. It doesn't really matter as long as you get the angle right on this. And what I propose is you can actually, because I know you have in the course here about scaling up and down the charts and such, which I think throws a lot of complication there. You can literally put this on a piece of A4 paper, An A4 piece of paper, the longest dimension is about 30 centimeters, 297 millimeters, and it's just for speed. So putting margins around that A4 piece of paper, you could say you could put 25 centimeters on there with a bit of a margin around it, and then you can just draw a scale of 1 centimeter equals 1 knot. So that means you could plot up to 25 knots on that piece of paper, and that'll cover you for most sailing situations, you see, and that'll do. And basically all we need is a speed here. Okay, that's our speed over ground for this given tide and boat speed. And then rather doing this thing where we're doing a distance divided by another distance and that gives us a time, let's stick to the standard speed equals distance divided by time. Okay, then we can go and rearrange that, so time equals distance divided by speed, so we're all aware with that, and that gives us a distance divided by a speed, so 8.6 miles divided by 6.8 knots, and that gives us 76 minutes. But if it gives us 76 minutes, we should go in and do another triangle, shouldn't we? Okay, so that is it. These are just the things that I discovered about how we're actually using the parallelogram method here, dodging the use of sines and cosine rules. That's actually what the principle of this method is. I don't blame you from hiding this because this can seem a bit off-putting to a lot of people. I think we should rather do distance divided by distance. We should use the speed equals distance divided by time. And then obviously we have the actual original method that I put in at the beginning. Okay, so do send me a message on this. If you want to talk about it, it is a better method in my opinion. I'm happy to be proven wrong because by being proven wrong, we move closer to the actual true way. So I'm happy for that. And do send me an email or get in contact with me about this. Thank you very much. This is for your consideration.